final one on descriptive biostatistics. And by the end of this, you must be able to construct a frequency table for both qualitative and quantitative data, produce a bar graph, pie chart, histogram, and polygons. I have removed some of the graphs, but all the necessary graphs, you must be able to construct them when you go through this video. Now, frequency tables. When we talk of frequency tables, basically we are talking of converting ungrouped data to grouped data. The whole idea is that ungrouped data is very difficult to interpret in terms of if we are to make any decisions. You can't identify silent features that are present in the data if by merely looking at grouped data. So to convert ungrouped data to grouped data, it's actually as good as creating a frequency distribution table. So a frequency distribution table is the grouped form of the data. So this slide simply shows that frequency distributions can be created for both qualitative and quantitative data. Now we are going to illustrate through an example how to convert ungrouped data to grouped data. In other words, how to create a frequency distribution table for qualitative variable. Remember from our previous discussions what qualitative data is and qualitative variable. So we are not going to go into that in this particular case, but it is assumed that you have a clear understanding of what qualitative data is. In this case, we have a sample of 30 farmers from Umsat region who were selected and asked how stressful their job is. And you can see the table here is a complete set of their responses. Each farmer is giving one response. Very stressful, somewhat stressful, none meaning the farmer is completely fine, is not stressed by his job. Now, if we are to make a decision in terms of whether the farmer likes their job or not by merely looking at this table, you cannot tell how many said they are very stressed by their job, and how many said they are somewhat stressed, and how many said they are not stressed at all. It is very, very difficult to make a decision by merely looking at this table. So the idea of creating a frequency distribution table is to be able to decide on whether, if we are to make intervention strategies in terms of boosting morale of farmers, we need to basically decide on whether they are stressed or not in their job. So if we go, this data can be summarized into a frequency distribution, and the result will be as shown in this table. You can see that our variable in this case is the stress on the job. And the stress on the job has got some outcomes, vary, somewhat, and none. So what you need to do is to put stress on the job as your variable. You produce a tally, and then you indicate the frequency. How many farmers said they are very stressed, somewhat, and none? So you can see here, the idea of producing a tally is to make sure that you don't run the risk of skipping a certain farmer who gave a response. So, but eventually on the frequency distribution table, we don't expect to see the tally column. So you need to get rid of the tally column so that we only have the frequency column as well as the variable column. So this is the final, this is the draft, so you don't forget to remove the tally so that you only have two columns showing the variable and the frequency. Now, from this frequency distribution for a qualitative variable, you can also go on to produce all the necessary qualitative graphs. Qualitative graphs includes the bar chart. You can see here, this is a pictorial visualization of that data which is displayed in the frequency distribution table. You can see the bar chart here. So from here, one can easily tell that a lot of farmers are somewhat stressed, but those that are very, they also follow the list, and very few are not stressed. You can see that bar is smaller. So this is the purpose of summarizing the data. Remember, the whole idea is to say after collecting the data, we want to make meaningful decisions based on the available information. So you need to process the data as part of data processing. Now, you can see from this bar chart that we have used frequency in the y-axis, but instead of using frequency in the y-axis, we can also use what we refer to as relative frequency, and we can also use percentage frequency. Now, relative frequency is calculated as the frequency of the category divided by sum of all frequencies. I want you to appreciate the word relative comes from in relation to. What is the frequency of this particular class? For those who say it is very stressful, for example, how many are they in relation to the total frequency out of 30? So we can calculate the relative frequency. So if we multiply relative frequency by 100, we get what we call percentage frequency. So we can then produce a bar graph of relative frequency against the job stress level, and we can also produce a bar graph of percentage against the stress level. So as an activity, I would like you to produce a bar graph, 1 for relative frequency and 2 percentage frequency using the data for table 2. And you must also produce a pie chart for the same data. I want you to bear in mind that pie chart is also very useful graph for qualitative variable. So that same data can also be represented in the form of a pie chart. If it is a research article or a manuscript, you don't need to use the same type of graph throughout. So you may either use a frequency distribution table, you can use a bar graph, you can use a pie chart. So using the same data, try to produce a pie chart for the same data. How do you go about it? Remember, you need first of all to calculate the relative frequencies. Now, once you have the relative frequencies, you don't multiply them by 100. Let me go to the pie chart so that you see in this pie chart, the total degrees here, this is a complete revolution, is equal to 360. So you ask yourself, how many said none? So you look at the relative frequency for those who said none. After getting the relative frequency for those who said none, you multiply by 360 in order to decide on this 20%. You do the same for vary and you also do the same for sum. If you do it correctly, you must be able to produce this pie chart, and you must know which specific tools, which specific mathematical tools that you need to come up with a pie chart. Definitely you need a protractor to measure the degree, those who said 20, those who said vary, and those who said somewhat. Now let's move on to grouping continuous data. Remember, we have covered the part of qualitative variable, but more importantly is also the ability to group continuous data into a frequency distribution table. Now what we have here is the data on yield in tons per hectare of pearl millet recorded by 30 farmers in 2019 in the Kavango region of Namibia. If you look at this table, it is very, very difficult to make any meaningful decision because the data is haphazard. It does not show any pattern, so you need to categorize this data into a frequency distribution table. So from the frequency distribution table, you are able to produce an array of graphs that are suitable for qualitative data, including the histogram, the ogives, that is the less than ogive and the more than ogive, and also the stem and leaf, the box and whisker, and so forth. So from here, we are going to show how to group this data. I want you to clearly see, I want you to see that, firstly, before you group the data, you need to identify the maximum, and you need to identify the minimum. I've highlighted here the maximum is 29, and the minimum is 5, and our total data points are 30. So the first thing is to determine the range. And from our previous discussions, we said the range is simply the maximum minus the minimum. So if you say 29 minus 5, we are going to get our range. Our range is equal to range equal to maximum value minus minimum. So we have our maximum is 29 minus our minimum is 5. If you do your calculation properly, you get 24 as our range for this particular data set. So the next step is to determine the number of classes. I want you to clearly understand, we don't determine the number of classes without using approaches. So there are basically two approaches. One is what is called the 2 to the k rule, and the other approach is called the stages rule. Stages rule is named after Herbert staging. This one was discovered in 1921 by Herbert, and it is referred to as stages rule. So we also have the 2 to the k rule. These two methods are simply used to determine how many classes are supposed to be used for a given data set. You see, when we talk of classes, we can say, for example, 10 to 20, 20 to 30, 30 to 40. These are 3 classes. But how do you decide on, I have to use 3 classes, I have to use 4, I have to use 5, I have to use it. As a general rule, it is encouraged to use 5 and above. But I want us to appreciate, firstly, the idea of the 2 to the k rule. Now, under here, you can see that 2 to the k rule simply says that choose the number of classes k such that 2 to the power number of classes must be greater or equal to the number of data points that you are given. Now, from here you can tell that the more the data points, the more the number of classes, and vice versa. So if you have got 10 values, you are going to use smaller number of classes than if you have got, say, 90 data points. In our case, we have got 30 data points. So in other words, what it simply means, our n is 30. What we want to find is k. This is what we want to find. So we are simply saying 2 to the power k must be greater or equal to 30. For those who have covered basic mathematics, you know how to solve this. How do you get k in this case? You have to introduce logarithms on both sides. In other words, the log of 2 to the k must be greater or equal to log of 30. In which case, you know the laws of logarithm. Log of a number a to the power m is the same as m times log of a. You know this rule. Log of a certain number a to the power m is actually equal to m log of a. These are the assumed knowledge. So here you will have your k log 2 is greater or equal to log 30. In which case you get your k must be greater or equal to log of 30 divided by log of 2. And you know how to get this from your calculator. You just punch that in your calculator. But if you decide to use the stages rule simply says the number of classes C must be given by 1 plus 3.3 log of n, where C is the number of classes, n is the number of data points to be represented. Now, using this, I will leave the stages rule for you to do a step by step and group the data. But I'm going to demonstrate in this video the use of the 2 to the k rule. So, using the 2 to the k rule now. 2 to the k, this is what I've illustrated. So you get your k being equal to 4.9, which is approximately 5. Remember, the number of classes is discrete. It cannot be comma something. It has to be an exact value. So if you get 4.2, it is recommended that you always round upward. You see, when we round 4.2 to the nearest whole number, we get 4. But in this case, the rule is that it is advisable to round that 4.2 to 5. I know a lot of people here, they will always try to round it to 2, to 4. Now, but here I've also illustrated using the stages rule, you will get approximately 6 classes. But verify this yourself to see that indeed you appreciate why the stages rule is giving you 6 classes. Now, range for the entire is equal to 24. So now, how do you determine the class width? How do you determine the class width? You see, we have managed to determine the number of classes, And using the stages rule, we are saying, K, we need about 5 classes. But how wide are these classes? You see, when we talk of the width of a class, if we say 10 to 30, the width of this class now is actually equal to 10. We are saying 30, the upper class minus the lower class. In our case, how wide must be the 5 classes of ours? So we need to go a step further. To determine the class width, we need to divide the range by the number of classes. In this case, we say 24 divided by 5, that will give us about 4.5, which is also approximately 5. You see, we have to round again to use 5 for convenience. Now, with that, I want you to pay particular attention in this case now. You go back to your data. What is your minimum value? Your minimum value is 5. Minimum value is 5. So you need to start from your minimum. Minimum value 5. So the next, because we said that the class width must be 5. You see, you count from 5. 5, 6, 7, 8, 9. You don't say 5 to plus 5. So you will say 5 to 9. Then when you say 5 to 9, the next class is 10 to, you see, let me show you here how you proceed. When you say 5 to 9, the next class, to get the next class, you say plus 5. 5 plus 5, you get 10. Here you say also 9 plus 5. This will give you 14. Then the next class, you say 15, because we are just adding 5 in the lower class, and we are also adding 5 in the upper class. It will be to 19. Then you take your 20, because we are adding 5. Here we will also add 5 to 24. How many classes do we have now? 1, 2, 3, 4. But we need 5 classes. So we are going to have 25 plus 5 here to 29. These are the classes that we have. And I'm sure this is what we are seeing here. 5 to 9, 10 to 14, 5 to 19, 20 to 29, 25 to 29. You do the tally system just like what we did for qualitative data, so that you don't skip any value to determine the frequency. And this is what you have. So you are encouraged to remove the tally column and put the correct title on top of the graph. See also our previous video where we looked at the general rules for graphs. You don't just produce a graph without a title. So make sure you put a correct title, what this table is all about. But I want you to appreciate something. These classes are called apparent classes. They have gaps in between. You can see that, for example, 9.5 is not included in any of these, either in the first or in the second. Because we are saying 5 to 9, 10 to 14. So a value of 9.5 is neither in the first nor in the second. So these are called apparent class limits. And I want you to see how do you convert apparent class limits to real class limits. To convert apparent class limits to real class limits, you need to calculate what we call lower class boundaries and also upper class boundaries. I'm going to demonstrate this in the next segment. So you can see here, we have our, our circle was supposed to highlight 10. So we have our apparent classes, and I want you to see how we have converted these apparent classes to real classes. So to do that, look at the lower limits. Let me still use this one. You just look at the lower limit of the next class and the upper limit of the previous class. So you subtract these two, that will be 10 minus 9. 10 minus 9 will give you 1. You divide this 1 by 2 to give you 0.5. So with your 0.5, you subtract 0.5 from each of the lower limits of the apparent classes. You subtract 0.5 from each of these classes. And you add 0.5 on each of these upper limits. These, in other words, you are getting the class boundaries. the lower class boundaries and the upper class boundaries. So that at the end of the day, you have 4.5. You see, we've said 5 minus 0.5 to get 4.5. 2, 9 plus 0.5 to get 9. You repeat the same process until you have these classes. These are called real class limits. The idea of converting apparent class limits to real class limits is to enable us to produce a histogram, to enable us to produce a cumulative frequency curve, and so forth. We don't use the apparent classes to produce any of these graphs. We need to use the real class limits. So we have the frequency here. I have also put a relative frequency column, just in case you want to produce a histogram of real classes against the relative frequency, not against the frequency, or a histogram of real class limits against the percentage frequency. So you can use percentage frequency, you can use relative frequency, or you can use the frequency in your vertical axis. Now you can see this histogram, and I'm sure you need to try this by yourself. So from the previous table here, you can see your frequency, the highest frequency is 8. So that will guide you in terms of what scale you must use on the vertical axis. And then also these values, the real classes, must guide you on what scale to use on your horizontal axis. So if you do like that, in this case, we can actually, this must be produced on a graph paper. 4.5 to 9.5. This 9.5 is here. You don't need to rewrite 9.5. So in other words, you just say 4.5 to 9.5 to 14.5 to 19.5 to 24.5 to 29.5. So against this, you mark the frequency for this class is 3, the other class is 6, the other one is 8, the other one is 8, and the last one is 5. This is 5. You can see here it's 5. So what I want you to do, instead of using the number of farmers, which is the frequency, the original frequency, you can actually use the relative frequency so that you have the class, the yield, against the relative frequency. You can also use the class against the percentage frequency. The relative frequency is actually very useful if your frequencies are too high. For example, you have up to 1,000 farmers. It is very difficult to have a graph paper or an appropriate scale to represent that. So you would always try to use the relative frequency. Now, a frequency polygon is very easy. Once you are able to produce a histogram, you just connect the midpoints of the histogram, and you get rid of the bars. What remains is what we refer to as a frequency polygon. So you connect the midpoints of the histogram. So a polygon is of two types. There is what we call an open polygon, and there is what we call a closed polygon. A closed polygon, we must have a line at the end here, connecting this end to the assumed midpoint, which is on the line y equal to 0 here. You just draw a line from this coming here, and here you also draw a line from here coming to this point just below the origin in this case. That is a closed polygon. So here we have this. Drawing a polygon from a histogram is very straightforward. Now, as an assignment, this assignment will be announced. The due date will be announced on Moodle. Use the grouped yield data to produce a less than and more than cumulative frequency archives. I'm sure there are so many sources demonstrating how to produce a cumulative frequency, less than cumulative frequency, and more than cumulative frequency. Produce a box and whisker plot using the ungrouped data. I'm sure we demonstrated from our previous class discussions how to get the quartiles, the lower quartile, the second quartile, and the third quartile, and also the minimum and maximum. So our box and whisker will have to show 5 measures of central tendency: the minimum, the lower quartile, the second quarter, which is also the median, the upper quarter, which is the 75th percentile, and the maximal. So how to calculate that, you know, we have covered that, how to do interpolation if required for ungrouped data. So repeat that process and produce a box and whisker plot. And you also know how to produce the box and whisker plot for, for grouped data. So in other words, you are required to get the lower quarter, the second quarter, the third quarter for grouped data, and also the range, that is the minimum value for grouped data and the maximum value for grouped data. Produce a stem and leaf plot using 1, the grouped data, and 2, the ungrouped data. We are still referring to the yield data. Each of the above graphs are to be produced manually and also using Excel. From all these graphs, these are produced from Excel. This one, I produced it from Excel. So I want you also to use the same data and make sure you are able to get that graph. And you must also do it manually. And the graphs must basically look the same. Thank you very much for this short video. And this marks the end of our descriptive biostatistics, where we have covered the calculation of measures of central tendency, the measures of dispersion for both grouped and ungrouped data, as well as the graphical techniques. We have an array of graphs. Make sure you practice and you know how to produce a number of graphs that are applicable for both qualitative data as well as quantitative data. Practice makes perfect. We'll meet next time where we are going to introduce inferential biostatistics, and our first part will be introduction to probability, and because probability theory now plays a key aspect in inferential biostatistics. Thank you very much. Meet you next time.